there, curious minds. Welcome to another deep dive. You know that feeling, right? You grab some really promising fresh produce or maybe that perfect loaf of bread, and then just like a week later, poof, there's this unwelcome fuzzy visitor. It's, frustratingly common. I know it well myself. I remember finding these beautiful damson plums once, totally full of promise for jam making, and then, well, before I even got started, they had this surprising fuzzy coat. Ugh. So today, we're diving into that whole unseen world. We've got our expert here to help us pull back the curtain on how fungi spoil our food and, crucially, what clever ways we fight back.
Hi there. Yeah, it's a challenge pretty much everyone faces, isn't it? And it's actually far more complex and I think fascinating than just, seeing a bit of mold.
Definitely seems that way.
So our mission today in this deep dive is really to give you a clearer picture of what food spoilage actually means, the sometimes surprising strategies fungi use to claim our groceries, and then look at the really impressive arsenal of methods we've developed to stop them.
Sort of a shortcut to getting clued up on this whole issue.
It's exactly from your own pantry right up to, well, global food systems.
Okay, I'm ready. We've definitely got some aha moments coming your way as we explore this microscopic world that's messing with our dinner plates. So let's get started. First off, when we talk about food spoilage, you might think it's pretty straightforward, right? Something looks bad, smells weird, tastes off, you just toss it. But that definition, it's not always quite so simple, is it?
No, not at all. I mean, sure, those visual cues, the texture changes, smell, taste, that's definitely part of it.
Yeah.
But what one person or culture considers acceptable can vary hugely. Think about fermented foods, cheeses.
Yeah.
We intentionally change them using microbes.
Good point.
But what's really key here, and maybe less obvious, is the scientific criterion. Food is considered spoiled, like non-negotiably spoiled, regardless of how it looks or smells, if it contains potentially harmful levels of mycotoxins.
Mycotoxins. Okay, that sounds pretty serious, something our senses just can't pick up.
Precisely. Yeah, these are invisible metabolites produced by some fungi, and they can be genuinely dangerous. The crucial thing to grasp here is that you really can't always trust your eyes or nose. Invisible toxins can make food unsafe, even if, say, the visible mold has been cut off or maybe processed out. Think about peanut butter made from peanuts that had some mold contamination earlier on.
Wow. Okay, that really changes things. So even if you're super careful, you might not know if something's truly unsafe, which makes understanding prevention even more vital.
That's it, exactly. It's a critical distinction.
So let's talk about the culprits then. Bacteria often get the blame for spoilage, right? Especially in wetter foods.
They do, yeah. Bacteria are big players.
Yeah.
Especially in things that are very wet or more alkaline.
But fungi are major players too, especially in other kinds of food.
Absolutely. Fungi are particularly good at spoiling drier foods or things that are more acidic. So think grains, fruits, jams, bread, that kind of thing.
And the scale of this problem, it's huge, isn't it? I read somewhere it's like a quarter of all produce harvested.
That's the estimate, yeah. Around a quarter spoils before it even gets eaten. It's a staggering amount of waste, globally speaking.
A quarter. Wow. Okay, so how do these fungi actually do it? Is it just one method, or are they more strategic?
Oh, they have several different strategies. Firstly, sometimes the damage starts way before you even buy the food. It's caused by plant pathogenic fungi that were already infecting the plant in the field. They just, continue their work after harvest, maybe in storage or even in your fridge, like an apple gets bruised, and that little injury becomes the perfect entry point for rot later on. Then a second strategy involves what we call necrotrophs, like Manulagia fructigena. It causes that awful soft rot in peaches and other stone fruits.
Right, I've seen that.
Yeah, these fungi don't just feed on already dead cells. They actually release toxins that kill the plant cells first before their fungal threads, the hyphae, even get there.
Whoa, so they're like actively creating their own food source by killing the cells.
Exactly. They create their own supply of dead organic matter. So they are technically saprobic, feeding on dead stuff, but they're pretty aggressive about making it dead first.
That's quite a tactic. What else?
Then you have many fungi, especially storage fungi, that are strictly saprobic. They only feed on matter that's already dead. But, and this is key, they often have these really unusual abilities that let them survive where other things can't.
Like superpowers?
Sort of, yeah. We call them tolerant. Some are zero tolerant. They can cope with incredibly low moisture levels, really dry conditions.
Okay.
Others are thermotolerant. They can handle high heat. Or the opposite, psychrotolerant, meaning they can grow at really low temperatures, even below freezing.
In the fridge, you mean?
Yeah, or even colder sometimes. And beyond that, some tolerate super acidic environments or even low oxygen, high carbon dioxide conditions. They're remarkably adaptable.
Okay, so it sounds like for a fungus to actually succeed, to spoil our food, there's a kind of checklist it needs to tick off.
That's a good way to think about it, yeah. A fungal wish list. First, obviously you need the fungus itself, spores, or little bits of fungal hyphae, what we call propagules or inocula. They have to be present.
Right. Step 1.
Step 2, they need food, a source of carbon, nutrients. Step 3, enough moisture, which is where this idea of water activity becomes really important.
We'll get back to that one.
Definitely. Fourth, the pH level needs to be tolerable for them. Fifth, they usually need oxygen, though we'll see some exceptions. And finally, sixth, there can't be any substances present that actively stop them from growing, inhibitors.
So it's a bit of a balancing act for them.
It is, but given how many spores are floating around literally everywhere, I mean, hundreds, thousands per cubic meter of air,
Wow.
completely keeping them out, excluding them, is just incredibly difficult. Almost impossible, really.
Okay, so if total exclusion isn't practical, what's the main plan B? How do we actually stop them?
Right, so that leads us to prevention, mainly through inhibition, stopping them from growing or killing them off if they do get in. We've come up with quite a few effective techniques, and they basically fall into two big categories.
Which are?
Those that kill or physically remove the microbes, and those that just inhibit their growth, slow them down, or stop them.
Okay, let's tackle the kill or remove methods first. I guess heat sterilization is the classic one, like canning, bottling.
Exactly. Heating food hot enough for long enough to kill off those fungal propagules. It's fundamental to canning, bottling, vacuum packing.
But you mentioned some fungi are pretty tough. Does heat always work?
Not always, no. That's the catch. While it kills many fungi, some molds are surprisingly thermotolerant. They can actually grow, not just survive, but grow at temperatures like 55, even 60 degrees Celsius. Think species of Aspergillus, penicillium.
60 degrees. That's pretty hot.
It is. And even more impressive, or maybe worrying, the reproductive spores, the ascospores of fungi like Biociclamis or Talaromyces can actually survive being heated up to 80 degrees Celsius for a short time.
80. Okay,
It's
that's
resilient.
extremely.
Yeah.
And here's the really crucial point about heat. Even if it kills the mold itself, it's often not very effective at destroying any heat-stable mycotoxins that the fungus might have already produced.
Oh, right. So you kill the fungus, but the poison could still be there. That's quite sobering.
It is. Dead mold doesn't automatically mean safe food if it was contaminated beforehand.
Okay, so heat's not perfect. What else is in the kill or remove toolbox?
Well, then there's irradiation. This is a more modern technique, quite promising. Food is sealed, then treated with gamma radiation.
Sounds intense.
It is, but it's very effective. It kills bacteria, fungi, insects, gives the food a really long shelf life. Now, there have been discussions about, does it reduce vitamins slightly or create free radicals?
Right, I've heard those concerns. Yeah, and those are things to consider. Free radicals, by the way, are unstable, but they break down naturally pretty quickly. But, from a global food security perspective, especially for people facing hunger, food with maybe slightly reduced vitamins is definitely better than no food at all or spoiled food. It's a powerful tool.
Makes sense. Any other methods in this category?
There's also filtration, but its use is pretty limited, mainly for clear liquids. Think beer, wine, some fruit juices.
Why only liquids?
Because to actually filter out microbial spores and cells, the filter pores have to be incredibly tiny, less than 1 micron. And filters that fine, well, they clog up really easily, especially with anything thicker than water. So effective for specific things, but not for, say, your bread or cheese.
Got it. Okay, so that's killing or removing.
Right.
What about the other approach, just stopping them from growing, inhibiting them?
Right, and this is often more common in practice. And the oldest method here is almost certainly drying.
Just taking away the water they need. Seems logical.
Exactly. Deny them water, they can't grow.
Yeah.
But here's the interesting part. You don't always need to remove all the physical water. It's more about making the water that is there unavailable to them.
How does that work?
This brings us to that concept we mentioned, water activity, abbreviated as AW. It's essentially a measure of how available the water in food is for microbial growth.
Okay.
We measure it by seeing how much moisture the food exchanges with the air around it in a sealed space. So if the air reaches, say, 85% relative humidity, the food's water activity, its AW, is 0.85. Pure water is 1.0.
And most microbes need a lot of available water.
Most need a very high AW, yeah. typically above 0.95 to really thrive, bacteria especially.
But fungi. I sense a but coming.
You guessed it. This is where fungi get really impressive. Some are incredibly zero tolerant.
Meaning dry tolerant.
Exactly. They can grow at surprisingly low water activities, much lower than most bacteria. Some yeasts and conidial fungi are among the most zero-tolerant organisms known on Earth.
Like, how low are we talking?
Well, for example, there's a fungus called Willemia sebi. It grows on things like saltfish, and it can handle an awe down to 0.75.
Wow.
Chrysosporium fastidium can manage 0.69. And the champion, as far as we know, is Aspergillus acuminatus. It can apparently grow slowly at water activities as low as 0.62.
0.62. That seems incredibly dry.
It is. And that explains things like, why your block of cheddar cheese, which feels pretty dry, can still get moldy in the fridge. Its awe might be low, but maybe not low enough for these specialists.
Oh, okay. And jams and jellies, they're super sugary. That must affect water activity too.
It does, drastically. All that dissolved sugar binds up water molecules, lowering the awe, creating high osmotic pressure. That definitely slows fungi down a lot. But even then, jams aren't completely immune, especially to zero-tolerant molds. That's why home jam makers are still taught to sterilize jars properly, maybe add a wax disc, seal it tightly, reducing awe helps, but it might not be the only protection needed. You usually need an awe below 0.65 to really stop fungal growth altogether.
Fascinating. Okay, what about the fridge? Refrigeration, that's everyone's go-to method. But you hinted earlier, it's not foolproof against fungi.
Right. It slows things down, extends shelf life, absolutely. But many molds are cycrotolerant.
The cold lovers.
The cold tolerators, yeah. They might not love it, but they can handle it. Many will grow, albeit slowly, at typical fridge temperatures, around 4 degrees Celsius. Some even grow right down at 0 degrees C.
Seriously? Like what?
Well, some penicillium species can grow at -2 degrees C. There's one called Cladosporium urbarum that can manage growth at -5. And even a fusarium species reported down to -7 Celsius.
-7. That's well below freezing. So the fridge is really just a temporary pause button for these guys.
For many molds, yes. It buys time, but it doesn't stop them indefinitely. For truly stopping fungal growth in moist foods using temperature, you really need a proper freezer, running at -18 Celsius or below.
Good to know. Okay, moving on. What about adding things to the food? Chemical inhibitors?
Yes, that's another very common strategy. And what's interesting here is how specific some of these chemicals can be.
How so?
Well, take calcium propionate. It's often added to bread dough. Why? Because it's quite effective at slowing down mold growth, but it has very little effect on the baker's yeast needed to make the bread rise. Perfect for baking.
Klaus.
Or sodium benzoate. It works well to inhibit both yeasts and molds, but mainly in acidic conditions like pH 2.5 to 4.0. So it's great for things like jams, fruit juices, pickles.
Okay.
Sorbates do a similar job, but they work effectively at slightly higher pH values, so they have different applications. And then there's sulfur dioxide used a lot for preserving dried fruits like apricots, and also for disinfecting winemaking equipment.
And are these safe? I mean, adding chemicals to food?
Many of these are substances that are also found naturally, or are very similar to natural compounds. Things like lactic acid and propionic acid, which you find in fermented foods and cheeses anyway, are considered GRAS. Generally regarded as safe food additives by regulatory agencies. We're essentially using targeted chemistry to give our food an advantage.
Right, leveraging nature's own defenses sometimes. Okay, one more inhibition strategy. What about excluding oxygen? You said most fungi need it.
They do, yes. Most fungi are aerobic. So methods that remove oxygen are very effective against many of them. Think canning, bottling again, the heating sterilizes, and the seal excludes oxygen. Also, sealing things with wax or storing food in modified atmospheres like tanks flushed with carbon dioxide or nitrogen.
But I bet there's a catch here, too. Some fungi aren't bothered.
There's always a catch with fungi. Some species are surprisingly tolerant to low oxygen. The classic example is Penicillium roquefortii, the mold that gives blue cheese its character.
Ah, Roquefort Stilton.
That fungus can actually grow quite happily at oxygen levels that are only about 10% of what's in normal air.
Wow.
And there are others, like Gleocladium roseum or Trichoderma coningi, that can grow reasonably well, even in just 1% oxygen. So to really stop all fungal growth by removing oxygen, you often have to reduce the levels dramatically, sometimes down to like 0.2% or less, which can be technically challenging.
Okay, so they're adaptable even when it comes to breathing. This is incredible. Right, now that we've got a handle on the fungi themselves and this whole arsenal of defenses we use, let's make it really concrete. How does this play out in the foods we actually eat? Maybe a quick tour through the grocery store aisles.
Sounds good. Let's start with cereals and nuts. Grains, seeds, nuts. If they're harvested properly dry and kept dry in storage, they're generally pretty safe from fungal spoilage.
The low water activity helps there.
Exactly. But the big danger comes if they get damp, maybe due to a wet growing season or poor storage. That's when you can get field molds like Fusarium species kicking in.
And fusarium sounds familiar. Mycotoxins again.
Yes, notorious for producing mycotoxins like zearalenone, T2 toxin, vomitoxin, really nasty stuff. And then in storage, if conditions are right, you can get storage molds like Aspergillus flavus or Aspergillus parasiticus,
And they produce?
aflatoxins. Among the most potent, naturally occurring carcinogens known, a really serious concern, especially in things like peanuts and corn in warmer climates. Rice, too, can get moldy with Aspergillus or penicillium, some of which stain the rice yellow and also produce mycotoxins.
So dryness is absolutely key for grains and nuts. What about bread, which starts dry but doesn't stay that way?
Right. Bread is a prime target once it's out of the oven. Common molds you see are the black pinhead mold, Rhizopistolonifer,
Ah, yes, seen that one.
the green spored Penicillium expansum, or the black spored Aspergillus niger. That's where inhibitors like calcium propionate really help extend shelf life.
Okay, moving to the sweet stuff. High sugar foods, jams, jellies, honey. We talked about water activity.
Yeah, traditionally, the sheer amount of sugar kept them safe, lowering the ON usually below zero point 0.7. But as you see manufacturers reducing sugar content now, maybe for calorie reasons or cost.
Right. Reduced sugar jam.
Exactly. That raises the water activity back up into a range where those really specialized zero-tolerant fungi can potentially get a foothold. Things like the Aspergillus glaucus group, Penicillium coralophyllum, Willemia sebi. So for lower sugar preserves, things like sterile filling or keeping them refrigerated become much more important.
Makes sense. How about vegetables? They seem like a mixed bag. Some last stages, others not so much.
They are quite variable, yeah. Things like cabbage, potatoes, turnips have pretty good natural resistance and storage life. Others, like, say, lettuce or ripe tomatoes, are much more perishable.
What are the common fungal issues for veggies?
Well, you see things like gray mold rot, often caused by botrytis. There's watery soft rot from sclerotinia, and various specific rots caused by Penicillium, Fusarium, Alternaria, Cladosporium, Aspergillus niger, Rhizopus. Lots of potential culprits depending on the vegetable and conditions.
But we also preserve vegetables, like pickling.
Absolutely. And fermentation's a great example. Turning cabbage into sauerkraut using lactic acid bacteria. The bacteria produce lactic acid, dropping the pH way down, creating an environment where very few other organisms, including spoilage fungi, can compete. It's a brilliant ancient preservation method.
Cool. Okay, what about fruits? They seem especially vulnerable, maybe because they're sweet.
They are particularly susceptible, yes. It's a combination of factors.
Mm.
High sugar content, usually acidic pH, which fungi often prefer over bacteria, and also the fact that fruit tissues are often ripening or senescing, meaning the cells are breaking down, making them easier to invade.
So what kind of fungi attack fruit?
Oh, lots. Botrytis cinerea causes that devastating gray mold, especially on soft fruits like strawberries. Penicillium expansum is a major cause of storage rot in apples, producing mycotoxins too. Gluosporium also hits apples. Then you have specific Penicillium species, P. digitatum and P. italicum, the green and blue molds that just destroy oranges and lemons.
Ugh, yes. The citrus molds.
And Manila brown rot is a huge problem for peaches, plums, cherries.
Mm.
Really turns them into mush.
And even canning fruit isn't foolproof, you said.
Right, because of those incredibly heat-resistant ascospores. Fungi like Bisaclamis fulva or Benivia can survive the 80°C heating sometimes used in fruit canning processes. They can then germinate and grow afterwards, spoiling canned fruits and fruit juices, sometimes producing gas that swells the can. They can also produce mycotoxins.
They really are persistent. Okay, last category. Foods of animal origin. Meat, eggs, fish, dairy.
Right. For fresh meat and eggs, bacteria are usually the first and main spoilers because of the high moisture and nutrient content. Fungi like Penicillium and Aspergillus species can grow, especially on cured meats, or it's stored poorly. And they are a concern because they might produce mycotoxins like cyclopiazonic acid or ochratoxin. Preservation relies heavily on refrigeration, vacuum packing, curing, or drying.
What about fish?
Fish, particularly if it's dried or salted, is quite vulnerable to fungal attack, especially by those zero-tolerant types we keep mentioning: Eurotium, which is the sexual stage of Aspergillus glaucus group, Scopularapsis, Penicillium, Willemia. Mycotoxin production, like ochratoxin A, can be a problem here too. Reducing water activity through proper drying and salting is absolutely critical.
And finally, milk and dairy.
Raw milk spoils very quickly, mostly due to bacteria. Pasteurization kills most microbes, and refrigeration slows down the rest. Those are key. Turning milk into cheese is itself a preservation method, extending the life significantly.
But cheese gets moldy too.
It certainly does. Cheese is commonly attacked by fungi, even in the fridge. Various penicillium species, like Penicillium commune, are common culprits on hard cheeses, sometimes Aspergillus versicolor. Again, spoilage is delayed by the reduced water activity compared to milk, by salt, sometimes by vacuum packing, and definitely by refrigeration. But those cycrotolerant and xerotolerant molds can still find a way eventually.
Wow, what a tour. It really covers everything in the kitchen. From, understanding that spoilage isn't just about visible mold, but these hidden mycotoxins, to seeing just how incredibly adapted fungi are. The heat resistance, the cold tolerance, the ability to survive dryness. It's kind of amazing.
It really is. Their biological versatility is incredible.
And then exploring all the clever methods we've developed to try and stay one step ahead, heating, drying, cooling, chemicals, removing oxygen. It definitely gives you a whole new appreciation for that perfectly preserved jar of jam or that loaf of bread that lasts the week. You realize what's gone into keeping it safe.
Absolutely. And if you sort of zoom out, connect this to the bigger picture, you see that preventing food spoilage is this constant, really dynamic interplay, doesn't it? It's about understanding the fundamental biology of these fungi
Yes.
and then innovating with our preservation techniques based on that knowledge.
A continuous battle almost.
In a way, yeah. And it's not trivial. It's not just about food looking good or tasting nice. It's fundamental to food safety, preventing illness, and also to global food security, minimizing the massive losses that occur between the farm and the fork, saving millions of tons of food every year.
A truly vital area of science then. So maybe a final thought to leave our listeners with. As our world changes, with climate shifts affecting growing seasons and consumer demands changing, maybe wanting less processed foods, lower sugar, less salt, what kind of new challenges might pop up? Could we see new types of fungal spoilers becoming more prominent, or maybe the old ones getting even tougher to beat?
That's a great question to ponder.
Yeah.
How will these resilient organisms adapt next?
Definitely something to think about. Well, we really hope this deep dive has given all of you a much richer understanding of this microscopic battle that's happening constantly, right in your own pantry and fridge.
It's been fascinating to explore. Thanks for joining us.
And on behalf of the Deep Dive team, thanks for learning with us. Keep those curious minds buzzing.